Hello, everybody. Come on in. I can take questions. We got 4 minutes for class starts, so feel free to ask me questions you might have. I'm just trying to get my stuff ready. Let me see if I can do a screen share already. All right, that's working. So I can also go ahead and stop that. We're good to go there. Stop share. You got some more people coming in. Noticing how bald I look in this camera view. Whoa, my hair. I used to have hair right here. It's gone. Still no questions, anyone? I got the chat open too. You can ask me questions that way if you want. All right. Okay. Still time to ask questions if you want to before class gets started. We got another minute or so. I'm just coming to the realization that I might be growing bald. It didn't look that bad before. I gotta shave it.
Did you get my email about the due date for the homework?
Yes, and I changed it. You talking about for? I think that was you that I remembered. Let's see, it's Wilkinson, right?
Yes.
Yeah, it looks like I didn't reply to it though. Yeah, where's that? Oh, there it is. Yeah. I'll go ahead and change that. It's not a big problem. In fact, I just went to change to make sure everything was okay a few minutes ago. Uh, Let me look at this real quick, see what I can do. So just so you know, guys, remember the homework is generally always due 11:59 on the Sunday before class begins. Sometimes I'll put the conceptual questions due Wednesday, or excuse me, due Sunday, and then make the actual homework questions due the Wednesday thereafter, or actually for your class, it'd be the Tuesday thereafter. Mom, Tuesday and Thursday classes have a different day. But right now I've got chapter 1 was due 8/29, which was last night. I'll go ahead. I'll be kind. I'm going to give y'all everybody to the 31st to do that. That does bundle up where now you've got, chapter 1 conceptual and homework due on the 31st. And then on the 3rd, if you wish to do the extra credits, that's physics primer and introduction to mastering, then they're going to be due on the 3rd as well. And then chapter 2 is due on the 3rd, both conceptual and homework. I think I'm going to go ahead and move chapter 3 homework, or excuse me, chapter 2 homework to be due on the 5th. So I just made that change. That should take care of your issue there, John. Anybody else? All right. So I did notice actually your test is okay, the practice test. I have practice test one up already. Our test will probably be opened up for you to start taking sometime next week, and then you'll have I think the due date was supposed to be the 10th. I'm going to double check my syllabus, but that's what I'm leaning towards you. So know that sometime next week, might even be tomorrow, I might open test one, and you're going to have it done by September 10th. That's what we're leaning towards. If I decide to make it a later date, I'll let you know. But right now, that's what I'm leaning towards. So that would be 11:59 p.m. on September 10th, which is a Sunday night. So looks like we got 16 people in here. Does anybody have any other questions before I get started? All right. Well, I'd started talking previously with you folks about graphs of position versus time and stuff of that sort. In fact, the last thing I covered, oh yeah, I didn't even get to that. The last thing I had done was cover I covered the actual relative velocity stuff, and I even gave you the formal formula for basically for using relativistically correct stuff. So I didn't really get to what I was thinking I had gotten to. So I'm going to start off now where we have to make some sense of motion. We have to get some ideas of what, velocity is, what speed is, what acceleration is, and that sort of thing. And I'm going to actually derive equations for you as well. So if you imagine for a second making a plot of position versus time, okay, I'm going to go ahead and share the screen. Almost forgot. I'm going to share the screen with my iPad. And just speak up if you have a question. And if it gets too commotiony or whatever, where I have to where it's getting too loud or something like that, then I'll go back to asking you guys to raise your hand or something, even, Zoom hand raising. But right now you can just blurt out if you have a question and just say, excuse me, Mr. Younger, such and such. All right, that because sometimes I don't always look at the chat as frequently as I need to, and I know I miss people's information or messages that way. So anyways, just keep an eye on that. Someone asked about which textbook to purchase. So if you're wanting a textbook that you need a physical copy of that you like that, I would say long as you have access to the 5th edition through MyLab and Mastering, which is the $129.99 package that allows you I don't know if it's 2 years or the life of that edition or whatever. That gives you access to the absolute 5th edition of the e-text. And that way, if I assign any problem out of the text, you'll have exactly the right problem listed there. But far as just for reading, there's a little difference between the 4th edition and the 5th edition, or even between the text of the 3rd edition and the 4th edition. So the cheapest one of those two you can find would be excellent to use for just reading a physical copy, but you're still going to have to have access to the 5th edition in case I assign something out of that. Plus, it gives you a little bit more of an advantage, specifically by recognizing the questions in the homework set. You can sometimes find them in the end of the chapter for chapter 5, and then you'd have, of course, the actual answers for the odd ones. So that can help you. So yes, you definitely need at least the ebook version of the 5th edition, but go as cheap as you want to find a written copy. So let's get started again. We're in chapter 2. I'm going to imagine a scenario where I'm going to walk some distance, and then I'm going to make some headway on trying to understand motion in general. So let's start off. I'm going to draw a vertical axis and a horizontal axis. The vertical axis is going to be X in meters, say, and the horizontal axis is going to be S in seconds. And I'm going to imagine each one of these squares is 1. So let's imagine, for instance, that I started walking at the position that you'd call X equals 0. And then after, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So let's say after 6 seconds, I had gone a distance of 1, 2, 3, 4, 5, 6 meters. So let's say after it took me 6 seconds to walk a distance of 6 meters. And let's say I did so that if I looked at my position after 3 seconds, I would have found that I went 3 meters. If I looked at myself after 1 second, I would have found I went 1 meter, in 2 seconds to be 2 meters, and 4 seconds to be 4 meters, and 5 seconds to be 5 meters. This would be a graph of that motion. Now, let's imagine that I did the same thing, but instead of going 6 meters in 6 seconds, I did 6 meters in 3 seconds. Now, again, in that case, I'm going to say I did half as far in half the time. So at 1.5 seconds, I would have been at 3 meters, and so on and so forth. When I do that, I could get, let's say, this other line here. Okay. So those are two motions. And the reason why I wanted to show you those is this is what Galileo defined as uniform or constant velocity or constant speed. So he's really the one that mathematically came up with the idea of speed and velocity. And he defined what we consider constant velocity as, let's take a time interval of say 1 second. And it can be any time interval, but the main thing is you pick one and then go with it. And Galileo would say an object going at constant speed / constant velocity will travel the same distance every second. Okay, so that's the definition of a constant velocity or constant speed. It travels the same distance for a given time interval. So like I showed you on that black graph, in 1 second, I went 1 meter. After 2 seconds, I went 2 meters, which means from 1 second to 2 seconds, that's 1 second, I covered another meter. And then from 3 seconds to 4 seconds, I covered another meter. And then from 4 to 5, I covered another, so on and so forth. So that's definitely the idea of constant velocity. And that's what Galileo gave us. Now, if we look at this and calculate, say, the slope, you can look at this and see the slope. And this is going to be m1 equals the slope equals, remember, slope formula is rise over the run. If you do that, you can see the rise at any particular point. If I chose, for instance, this point and this point, then the rise would have been 7 minus 4 meters. So I'll put the meters on the side just so we can see it, because that's what the vertical axis is. And the run is, of course, from 7 seconds, actually 2 7 seconds from 4 seconds. So minus 4 seconds. So 7 minus 4 is 3, and 7 minus 4 is 3. So I get 3 meters in 3 seconds, are 1 meter per second. Now, if you notice that unit, you see the unit is units of like meters per second. And if you were to look at, for instance, a speedometer on your car, you'd see that the units they're using are kilometers per hour, or it'll say mph on a lot of them. So I'm referring specifically to a picture in your textbook where they actually write on the inside of the speedometer the kilometers per hour in red, and they listed as kilometers divided by hours, which is perfect. That's what I want you to think of, is that's how you calculate speed, or at least average speed. Average speed is the distance traveled divided by the time taken. And of course, that means the unit should come out in like meters per second, or miles per minute, or miles per hour. In other words, the distance divided by time. Now, if we look at this other one over here, we can do a slightly different calculation. It's still calculating the slope, of course. But in this case, we're going to get a slope, m2 is equal to, again, rise over run. In that case, let's say, I'm going to take it over the whole, I showed it over a small part, but I'm going to take it all the way from the 6 second mark all the way to the 0 second mark, or excuse me, from the 3 second mark all the way to the 0 second mark. So I'm going to say 3, actually wrong part. I was getting ready to put the time up at the top instead of the distance. So I'm going to take 6 meters minus 0 meters, and I'm going to divide that by 3 seconds is the final, minus 0 seconds. So in this case, I get 6 meters per 3 seconds, which is 2 meters per second. Again, we've got a slope that has units of velocity or speed. And that might get you to think that maybe that is it. And in fact, it is. We will, at least in this chapter, sort of be using speed and velocity interchangeably. Next chapter, we'll learn that velocity, starting with a V, is a vector quantity, and speed, which starts with an S, is a scalar quantity. Notice the scalar and speed both have the same letter, and the velocity and V both have the same first letter as well. So that's a good little mnemonic for you. The average speed, and normally we indicate average with a bar, the average speed is actually supposed to be x minus x0 over t minus t0. We almost always call t0 0. So you could also write it as x minus x0 over t. That works fine as well. But that's the true definition of average speed. And in some sense, it's the true definition of average velocity. Now, in the sense that I'm talking about that it's not, specifically when you take the average velocity, you're supposed to subtract a vector we call the position vector. So you'd have a position vector for time t equals 0, and you'd have a position vector, which you can just represent, by the way, as an arrow, and that sort of makes some sense. So you draw it from the origin of your coordinate system to where you are initially at t equals 0. Then you draw another position vector from the origin of your coordinate systems to where you are after, say, 3 seconds or something like that. Now, what you're supposed to do then is you take the final position vector minus the initial position vector, and then divide it by the time taken, and that will give you the velocity vector. We haven't yet learned about adding vectors and subtracting vectors, so that's not that big a deal. But if you think about it this way, imagine, a goober little kid in, 3rd grade or whatever is playing t-ball or something. And I choose the goober wording specifically because I want him to do something that you're not supposed to do. Namely, he or she gets ready to hit a ball. And when he hits the ball, he's actually standing on home plate. Okay. At that point, he takes off running. He runs to first. He runs to second. He runs to third. Kids are dropping balls. Other kids are tackling other kids. It's just the chaos that you'd see at a little league game that's really so fun to watch. And then he rounds third and ends up going home. And then, of course, touches the plate again. At that point, basically the initial position vector and the final position vector would in fact be exactly the same thing, because he left from a point on the plate and returned to that point on the plate. Therefore, his displacement, his change in position, would be a 0 vector. So the average velocity would be 0 vector divided by however much time it took. So that's the big difference between average velocity and average speed. But other than that, you can sort of often pretend that speed is the magnitude of the velocity. And in that sense, we're never going to have a negative speed, and we're never going to have a negative magnitude of any vector for that matter. That's just the nature of how this is going to work out. So we have an average speed. Now, what if instead of that nice curve that I had there, what if I had a more, I don't know, random type of motion? So let's draw a more random type of motion. I'm going to draw a vertical axis. I'm going to draw a horizontal axis. Again, I'm going to make these axes x in meters and t in seconds. And I'm going to treat each block as one unit again. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7. So I'll outstand that one to make sure the 5 is easy to identify. 1, 2, 3, 4, 5. So I'll make that line a little bigger again, so that we recognize that as 5. We recognize this as 5, and that'll just be a little easier for us when we're quickly looking. Now, what if, for instance, the position versus time graph looks like that? Okay, and let's say you wanted to know the velocity let's say you want to know the average speed or at, let's say, 2 seconds. Well, what you might think is, okay, here I am at 2 seconds. And if I wanted to take the average, I need to find the position at 2 different places because that's how I take average. So maybe I do another point over here, and then I could connect that with what's called a secant line. Now, I was just still in my class. I never got around to checking it. I don't know why. I didn't know why they called it a secant line. But it turns out that secant in Latin, I think it's secare or something like that, really means to cut. So it's a line that cuts through a curve and hits it in 2 places. That's what a secant line is. So we could, in principle, say, based on these 2 points, I could say S average is equal to the slope. And I think you'd see that that calculation would be rise over run. Clearly, the rise, according to this, looks to be about 4.0 meters minus, let's say, 2.8 meters. And then the time for that is at 5 seconds was what the final time was. So I'll put 5.0 seconds here. And then the initial was at 2.0 seconds. So I'll do that. So 4 minus 2.8 is 1.2. And then that's 1.2 meters divided by 3.0 seconds, which is 0.4 meters per second. Okay. So that seems to work fine. But I think you could tell that, in fact, you're going quite slow. Remember the steep line that we did above? That one was going pretty fast. It had a velocity of 2 meters per second, and the line was really steep. The black line, however, was going at 1 meter per second, and it was steep too, but not nearly as steep as the other one. So if you look at the slope at the 0.5, for instance, this slope right here, whoa, I would definitely did not mean to do that. Okay, this slope right here looks essentially like m equals 0, whereas this slope right here does not look like m equals 0. Okay, you could actually sort of work it out. Maybe if I came to here and here, I'd say m is about, that distance is 5. Let's say all the way down to here. This distance is 0.5. So I'd say m is about equal to 5 minus 0.5 meters divided by, now the time that I was looking at that 5 was about 4 seconds. So I'd say 4.0 seconds minus 0 seconds. So that'd be 4.5 over 4. 4.5 over 2 would be 2.25. And then 2.25 over 2 would be 1.125. So this is 1.125 meters per second. Okay, again, assuming that slope. So what we might want to do if we really want the instantaneous velocity is we might want to convert this secant line to a tangent line. And the way you do that is you're going to call this quantity right here t, and you're going to call this quantity from here to wherever you're at delta t, so that the whole thing is t plus delta t. And we will slowly allow delta t to get smaller and smaller in a limiting type process. So I'm going to represent that with a series of red lines. So this is the initial case, then it'll go there, then it'll go there, then it'll go there, then it'll go there, and there, and there, and there, and there. So if you do that, you'll realize that you can take the limit as delta t approaches 0 of delta x over delta t, which is really the formula for the slope. And that turns out to be v instantaneous. And of course, the limit as delta t approaches 0 of delta x over delta t is just dx dt. So that's a very important formula, and it's fundamental to physics, as is this formula right here, which is the average speed and sort of the average velocity is the distance traveled divided by time taken. And I'll put right here, sort of, because we have that caveat about the little kid running around the bases. Okay. In this case, delta is not what I would call the uncertainty. You'd sort of say, hey, I would really like to measure such a small time interval that the velocity doesn't change very much. So in order to define a line, you need 2 data points, period. There's 2 points in space is what it takes to define a line. So no matter what, if you're going to try to find the slope of a line, you need 2 points to just define the line. So a t and a t plus delta t provides you 2 different time points, and therefore 2 different points in space. So that's why you're doing that. And if the time interval, the delta t that we've chosen is not small enough, then like you see on this graph, the tangent line, those lines that are actually parallel and touching the graph at certain points, that tangent line is not parallel to the secant line. But if you keep making that secant line over a smaller and smaller interval of time by decreasing delta t, then eventually you'll get so close to the same point t, in other words, the leftmost t, which seems to be at 2 seconds, you'll get so close to that that you really can't tell the difference. And in fact, the slope looks constant through that whole interval. So if I was able to zoom in on that particular data point, and only look at from 1.99 seconds to 2.01 second, you would see that that's more or less just a straight line, and 2 dots on it would be enough for us to define that line. So that's the actual process, is we're trying to get basically an idea of how to find the instantaneous velocity. So it doesn't actually have to be the full calculus process where you let delta t get 0. But if you want, say, 3 decimal places, you might find that 1/10 of a second is plenty good. Meaning if you do 1/10 of a second, you draw a secant line to that and you get a slope. And then you say, okay, well, let's try 100th of a second, and you draw a secant line and you take the slope and it gives you the exact same slope. Then you've clearly gone close enough, right? It all depends on how many decimal places you want. So that's the actual velocity definition. And if you had, for instance, a function x of t, you could take the derivative of it, and that would be the function v of t, the velocity as a function of time. Okay, so that's what that kinematic equation gets you. Now, if I wanted to talk about acceleration, I would really like you guys to think in terms of some parameters that a car dealership might tell you if they want to impress you with a car's acceleration. Now, there's like 3 or 4 different numbers that students guess at when I tell them that. And it's not so much a number that I'm looking for. It's almost like an experimental result that I'm looking for. So can anybody offer, either by chatting or speaking out, a number that you think might be relevant to a car's acceleration?
Like a 0 to 60 time?
That's the perfect one. Yeah. So a lot of people will say torque. That is certainly relevant. A lot of people will say horsepower. That's relevant. Some people will say horsepower to weight. That's a relevant issue. Some people even say, well, it depends on the RPMs, which it does if you're in a particular gear, and what RPMs you have. That all matters, right? So yeah, but honestly, the 0 to 60 is the perfect one. And in fact, what I'm going to do is I'm going to take some data from the old Mustangs that were around in the 1960s. And this was actually a pretty good thing. You would say a Mustang, and let's say 65 Mustang, went 0 to 60 in 4.00 seconds. Okay. That is really the archetypal vision of acceleration. So acceleration is not a change in speed. it's technically a change in velocity. So you're accelerating anytime, when we learn about vectors, it'll make more sense. But anytime you change the direction you're traveling, or anytime you speed up, or anytime you slow down, those are all accelerations. Now, to calculate what the acceleration is, you need to figure out how much the velocity changes per unit time. So what we're looking at is just like when we calculated v instantaneous, we took the instantaneous rate of change of x. So we're going to do the same thing with acceleration. We're going to take the instantaneous rate of change of the speed or velocity. So to do that, what I'm going to say is the acceleration on average would be v minus v naught over, again, you could write delta t here, but we're almost always going to just write t0 equals 0. So I can just put delta t down here, or just t. So that's what I'm going to put, is just t. So for this particular case, the final velocity was 60 miles per hour minus the initial velocity in miles per hour divided by the time, which was 4.00 seconds. Okay. Now, if you take 60 miles per hour minus 0, you get 60. If you divide that by 4, you get 15. So it's going to be 15.0. And I'm going to pretend that 60 was 60.0. So I'm sort of skipping some sig fig stuff right now. But that turns out to be 15.0 miles per hour per second. And I really like saying it that way, miles per hour per second. And when we start learning acceleration, you'll know the units are technically meters per second squared, but I would prefer you to say it as meters per second every second, or meters per second, because that gives you some understanding. Let me show you exactly what that understanding is. So let me draw another coordinate system. I'm going to draw a coordinate system right here, say. And I'm going to say, let's say this is, I'm not even going to, actually, I'll just draw it like a cars here. So right here at t equals 0 seconds, the velocity is in fact, let's assume this is, each block is 10, and this is in miles per hour, by the way. Okay. So at, t equals 1 second, let's say this is 1 second. This is 2 seconds, 3, 4, and that's 5 seconds, like that. So I've actually divided it up and made 2 squares be a second. So at t equals 0, its velocity is 0, because he said it started from 0 to 60, right? So it's 0 to 60. But after 1 second, assuming, if we assume the acceleration of the Mustang was constant, and it almost certainly is not, okay, this is what we get. We would get, after 1 second, it would reach a speed of 15 miles per hour. After 2 seconds, it's going to increase another 15 miles per hour, which would bring it up to 30 miles per hour. So after 2 seconds, I'm going to be at that dot. And then after 3 seconds, it's going to be at 45. So I'm going to bring it right there. And then finally, that would be 50. And this would be 60 right here. Okay. So it's actually going to be, after 4 seconds, it would be right here. And that would be the graph of velocity versus time. So I could imagine drawing a line of best fit, and it would go right through those points. I missed it a little bit, but you see what I'm saying. Okay. So if the acceleration was truly constant, an acceleration of 15 miles per hour per second tells you, oh, that's sort of equivalent to changing your speed by 15 miles per hour each second. So after 1 second, you're going 15. Then after 2, you're going another 15, which makes 30. After 3, you're going another 15, which makes 45. And after 4, that makes another 15, which is 60. Okay. Now, as I said, you probably recognize that a more realistic curve for a Mustang might be something like there's a little lag for just a split second, and then it rapidly increases and goes like that. Actually, it goes like that. Let me completely undo that. So it's going to be a little lag, and then it's going to rapidly go like that. But once you reach up to that 60 miles per hour, you know that if you're going 60 miles per hour, unless you're in a really, really powerful vehicle with a really, really high gear ratio, if you hit the accelerator really fast, you do not speed up very much at 60. So that red graph might be a more realistic graph. But let's look at what the slope is in this case. So in this case, the slope is 15 miles per hour. And then, of course, the run over here is going to be 1 second. So M is equal to 15 miles per hour per second, which is 15.0 miles per hour per second. So now you probably are reaching the conclusion that just like this, here's the two new kinematic equations. I'm going to say A bar is V minus V0 over time taken, and I'm going to say A instantaneous is equal to the limit as delta t approaches 0 of delta V over delta t, which I think you recognize as just dv dt, which is also d2x over dt squared. So that's the two new equations that we have hopefully made some sense of just by thinking about everyday life and whatnot. So do y'all see what the instantaneous acceleration is? Okay. Now, most of the problems we'll solve will be problems of the nature where the acceleration is a constant, but we are going to give you questions where the acceleration is not constant. So let me give you a synopsis of what we figured out so far. It turns out if you have x of t, you can get to v of t by taking a derivative, d by dt. And if you have v of t, you can get acceleration by taking a derivative, d by dt, and that'll give you a of t. Now, anybody want to guess? If I have a of t, what would I have to do to get v of t?
Take a derivative.
Integrate.
There you go, integrate. Yeah, that's part of the fundamental theorem of calculus is we learned that the antiderivative and the derivative were opposites. That's why we started off in calculus. You first did derivatives and then you did something called the antiderivative because they wanted you to understand that they are opposite operations. So if my arrow had to go the opposite way, I'm going to take the integral of a of t dt. And similarly, if I wanted to go from a velocity as a function of time to a position as a function of time, I'm going to integrate again. So this would be the integral of v of t dt. So that's a graphical representation of what we need to know. Now, I will tell you, if a equals a constant, then that really is a bad looking word, then. So if a is a constant, then the average velocity can also be found v plus v0 over 2. So that's another equation we can use. But again, that one's only true if a equals a constant. And the reason you can see that is a equals a constant is a graph like this bottom graph here, where I have velocity versus time. Now, notice the velocity is actually changing. That blue line is the velocity changing because you see at 1 second, the velocity is 15. At 2 seconds, it's 30. At 3 seconds, it's 45. At 4 seconds, it's 60. That red curve is a curve where the velocity, where the acceleration is changing as well as the velocity, because the acceleration is the slope of the graph. So you can see, for instance, right here, the slope of the tangent line is pretty high. Right here, it's not so high, and it's almost zero by the time you get here. So that's a non-constant acceleration. But if you want to find out what the average velocity is, then all you have to do is take, say, the velocity at this point and the velocity at this point and add them and divide by 2. Okay, that's another helpful kinematic equation we're going to use. And I'll write them all together when I'm finished doing this. But before I do that, I want to take what we know and make something out of it. So let's start off with a very simple problem. Let's say, I'm going to start a new problem right here. I'm going to say, actually, let's not write in cursive because I know that's a bit of a issue. Not everybody's learned that. Let's say, if the acceleration of an object is 3.00 meters per second every second, and its initial velocity is v0 equals v of t equals 0 equals v of 0. Let's say that's going to be 1.00 meters per second, and its initial position is x0 equals x of 0 is equal to, let's say, negative 2.00 meters. Okay. Then what is v of t, x of t, and v average from t equals 1.00 seconds to t equals 3.00 seconds. So this is a pretty big involved example. So let's show you how to do it. Now, I usually just started doing this with symbols in my classes, but I've found that students aren't able to come up with the idea too well when it comes test time. Because so I ask you very specific questions on the practice test, and it'll be stuff like, the acceleration is 3t plus 92, and they'll give you some other data, and they'll say, what's the velocity as a function of time, or what's the position as a function of time? Or they'll ask you that third question, what is the average velocity from t equals 1 second to t equals 3 seconds? So I hadn't been getting good success on that, so I'm trying something new. So let's try it now. So here's our solution. What I know is that A is dv dt. So I'm going to take that and I'm going to say 3.00. I'm going to leave off the units because that'll make it a little more confusing and hard to follow. So I'll just leave them off, and I'll remind you what they are from time to time. So I'm going to say 3.00 is equal to dv dt. That's an equation we can start with. Now, I'm allowed to do anything to an equation long as I multiply, long as I do the same thing to both sides. Of course, there's the caveat that that thing can't be multiplying by 0 or dividing by 0. Okay, so I'm not going to do that. But what I am going to do is I'm going to first off give myself a little bit more space. And actually, maybe not that much. Yeah, I'll do it this way. Hold on. Whoa. Okay. So now what I'm going to do is I'm going to multiply both sides by dt. And then I'm going to take an integral. And I'm going to take the integral from t equals 0 to t on this side. And I'm going to do the same thing here, t equals 0 to t on this side. Now, that's in parentheses, that's in parentheses. Maybe that'll make it a little easier for you to understand. But hopefully what you see is the integral of 3 dt is just 3t. So I'm going to say this is 3.00 t. Now, if I evaluated at t equals t and then and subtract from that at t equals 0, I get 0 for the t equals 0. So that's the whole left side, period. Now, the right-hand side is basically a version of the second the fundamental law of calculus, or the fundamental rule of calculus, which says that the integral of the integral of a derivative is the original function. So that's the fundamental theorem of calculus. We're going to take that and realize, oh, then I'm just going to get v of t here. So I'm going to get v of t minus the v at 0, which we said was 1.00. So I'll say 1.00. And here for a second, I'll put that unit in there so you can see that we are subtracting actual number that has the same units as the v of t. Remember also that the 3 is meters per second every second. So when you multiply that by a time in seconds, you just get meters per second. So the left-hand side works as well. So now what I can do is I can write v of t is equal to 3.00 t plus 1.00 meter. Well, I'll just leave off that because we're trying to do it without units right now. But you know what the units should be. And in fact, I've now found v of t for this problem. Any questions on that? Okay, pretty straightforward, right? And notice how I had to use one of the data points. What we're solving here is a second order differential equation, because in principle, the acceleration is not just dv dt, which would be a first order differential equation. The acceleration is d2x over dt squared. So it's a second derivative, which means it's a second order differential equation. And the rule is, if it's a first order differential equation, you need one initial condition, like v at t equals 0. If it's a second order differential equation, then you need two initial conditions, like v at t equals 0 and v at t equals 4 seconds. That would work. Or v at t equals 0 and x at t equals 0. That would work as well. Or you could have x at 3.0 seconds and x at 4.0 seconds. Or you could have v at 3 seconds and v at 4 seconds. You need two pieces of data. Okay. Now that we have that, we can make use of the fact that v of t is actually dx dt. So we can use that for the next step. And in this case, I'm going to write 3.00 t plus 1.00. And I'm going to do the same thing I did before. So I'm going to multiply it by dt on both sides. And I'm going to do an integral. So this side is going to become dx dt in parentheses dt. Again, I'm integrating from t equals 0 to t, and I'm integrating from t equals 0 to t. And now I've got 1/2 of 3.00 meters per second per second. I'm putting the units back in so we can really see what's going on here, times t squared plus 1.00 meters per second times t. And that's equal to v of t, or excuse me, x of t. That's equal to x of t minus x at 0. So x at t equals 0, we said was negative 2.00 meters. So that's going to be plus on this side. When I solve for x of t, then I'm going to get x of t is equal to, why did I write 1/3 there? I was supposed to write 1/2. Oh, I know, because I was looking at the 3. Hopefully y'all already caught that, but here it is. Okay. So this is going to be 1/2 of 3.00 meters per second every second times t squared plus 1.00 meters per second times t minus 2.0. I did not like the way that wrote it. Minus 2.00 meters. So we now have the position as a function of time, right? Now for part C, we really wanted to find the average velocity. So the average velocity, this is a constant acceleration, so we could use that formula if we wanted to, but I'm not wanting to do that. I'm going to say V average is equal to x minus x0 over t. Well, since I asked for 3 seconds and 1 second, x at 1.00 seconds, I think you can see is t squared with t equal 1 second. It's just going to be 1. So it's 3 times 1/2, that'd be 1.5, plus 1, that'd be 2.5, minus 2 would be positive 0.50 meters. Similarly, x of 3.00 seconds is going to be 3 squared is 9. So that's 9 times 3 would be 27. Notice that works out to be meters, period. That's 27, and then multiplied by 1/2 would be 13.5. So we got 13.5 there. And now I'm adding 3 because 3 times 1 is 3. So that's 16.5. Now I'm subtracting 2. That gives me 14.5 meters there. So now I can say V bar, sorry, I left the bar off of that equation a second ago. I can say V bar is 14.5 meters minus 0.50 meters divided by 3.00 seconds minus 1.00 seconds. 14.5 minus 0.5 is 14, and 3 minus 1 is 2. So this is 7.0 meters per second is the average velocity between t equals 1 second and t equals 3 seconds. Any questions on that? All right, so that's a very typical
Where'd you get the
scenario. Yeah, go ahead.
my bad, where'd you get the minus 2 meters for x of t?
Because when I said up here in the top, I said x of 0 is equal to
Oh, negative 2 meters. That's right.
negative
Okay.
2 meters.
Yeah.
So that's where that came from. You can see I put it in right here. And then, of course, when I pulled it over there, it was positive here. It became negative over there. Does that make sense?
Yeah, it was right there. Thank you.
No problem. All right. So that's a very typical scenario. And you might even recognize this equation. That x of t that I wrote, that's 1/2 at squared plus v0t plus x0, really. That's one of the kinematic equations that we're going to use this semester. And it's only valid for constant acceleration, which is what I had there. So in general, we could do that without actually using a number, and that's what I'm going to do. So I'll blow through this really quickly. I'm going to say A is equal to a constant. I'm going to say V of 0 is equal to V0, and I'm going to say X of 0 is equal to X0, and I want to find V of t and X of t. Solution. So this is another example. So the solution here is going to be A equals dv dt. That's going to give me the integral of A dt is equal to the integral dv dt, t equals 0 to t equals 0 to t. That's going to give me a t. And of course, t equals 0 gives me 0. So that would be minus 0. And the other side, this is going to give me v of t minus v0. So I now have v of t is equal to v0 plus at, which we normally would just write as v equals v0 plus at. I think you can see that that is, in fact, one of our kinematic equations, but it also happens to be the definition of average acceleration, like that. Okay. Now I can do the same thing. I'm going to say v of t is equal to dx dt. So this is going to give me v0 plus at integral dt is equal to the integral dx dt t equals 0 to t equals 0 to t. In this case, I'm going to get 1/2 at squared plus v0t is equal to x of t minus x0. So x of t is equal to 1/2 at squared, which is what we derived the other day with dimensional analysis, but we didn't have that 1/2 in front of it. But I did correct you and let you know that. But we also got a linear term that appears if the velocity's the initial velocity is not 0. And then we have a plus x0. This can be written also as x is equal to 1/2 at squared plus v0t plus x0. And that is another one of our kinematic equations. And this is for a equals a constant. And this is for a equals a constant. In other words, these equations are only valid for a equal constant. Notice I did not point that out for the a average that I wrote to the right in red there. I don't have to have that for that. That's just the definition of average velocity. Or excuse me, average acceleration. So I'll write that's always true. So I've now gotten some nice kinematic equations. V equals V0 plus AT. I've got x equals 1/2 AT squared plus V0t plus x0. But what if I want to know how far it's gone and I don't have the time? Maybe I have the final velocity. Well, I can do that by using this first equation. I'm going to call this equation 1. I'll call this equation 2. I'm going to solve this equation 1 for t, and I'll get t is equal to v minus v0 over a. And now I'm going to plug this t in 2. So now I'm going to get x, and I'm going to go ahead and pull the x0 to the other side. I'll say x minus x0 is equal to 1/2 a times v minus v0 over a squared plus v0 times v minus v0 over a. And that's what we have so far. Now, I can see that I'm going to be squaring that v minus v0 over a. So the denominator is going to be a squared. That's going to cancel out the a to the left, and it'll just leave a single 2a in the bottom. So now I'm going to get basically v squared minus 2v v0 plus v0 squared, all that divided by 2a. Now, on this next term, I have an exponent of a, not 2a. So I'm going to multiply by 2 over 2, and that will give me 2v v0. Notice the v0 has to be distributed through. So the v0 times v is what I have here. And then I multiplied it by 2. And then minus V0 squared. Oops, I was supposed to multiply that by 2 too. Minus 2V0 squared. And then, of course, I multiplied the bottom by 2 as well. Now I've got two fractions with common denominators, so I can start adding them up, and I get V squared minus 2V0 plus V0 squared plus 2V0 minus 2V0 squared, all of that over 2A. You can see now that clearly the 2V0 cancels out with the negative 2V0, and the V0 squared minus 2V0 squared is going to give V squared minus V0 squared over 2A. So now I can finally write x minus x0 is equal to V squared minus V0 squared over 2A, or V squared is equal to V0 squared plus 2A x minus x0. So that's another kinematic equation for us. And again, that's for A equals a constant, meaning it's not valid if A is not a constant. Okay. So all of these are our kinematic equations. We'll use them over and over. I want to show you one more example that's a little more difficult, because this is the kind of thing your book will do. So let's say A is equal to, let's actually change the color. I'm going to say A is equal to 3t plus 4, and that explicitly has units of meters per second every second. So you can see that the 3, in order for this to be true, since I've got to put in t in seconds, the 3 must have units of meters per second squared, and the 4 must have units of meters per second, okay? And I'm going to say V of t equals 0 equals V0 is, in fact, let's say 4.00 meters per second. And let's say x of 0 is going to be negative 5.00 meters. So that's just some stuff I made up, but I could ask you from that. Actually, I don't know what's going on here. I'm having a hard time drawing a decimal. Okay, so at this point, I could ask you V of t equals question mark and x of t equals question mark. So let's do that. So using A is equal to dv dt, actually, I'll write it this way. 3t plus 4, ignoring units for a little bit, is equal to dv dt. Multiplying both sides by dt, integrating. T equals 0 to t, t equals 0 to t. That gives us 3/2 t squared plus 4t is equal to V of t minus 4.00 meters per second. I'm not going to use that unit anymore. I'm just showing it to you that one time. So I now have V of t is equal to 3/2 t squared plus 4t plus 4.00 meters per second. Actually, I want to leave that off again. Sorry. Okay. So that's part of the answer. Now I'm going to say 3/2. Oops, I don't want that color. Now I'm going to say 3/2 t squared plus 4t plus 4.00 dt is equal to dx dt. In other words, I'm doing just like I did before. Now I'm going to integrate from t equals 0 to t and integrate from t equals 0 to t. Again, I just go through the process. This gives me 1/2 of, notice when I integrate t squared, that becomes 1/3 t cubed. So that 1/3 is going to cancel out that 3. So I get 1/2 t cubed plus 2t squared plus 4 point, or let's just call it 4t. All that's going to be equal to, oops. Make that a little bit better. Okay. Now all that's going to be equal to x, dang it. All that's going to be equal to x of t minus 5.00 meters. I won't write that unit again. I'm now going to say x of t is equal to 1/2 t cubed plus 2t squared plus 4t plus 5.00, or just plain 5. And in this case, we know the unit should come out in meters. So that 1/2 must have units of meters per second cubed. That t would or that 2 would have units of meters per second squared. And that 4 would have units of meters per second. And that 5 would have units of meters. Any questions on that? All right. So time's actually up. You guys are, of course,
I have a question.
go. Yes, go for it. Last, like I said, I'll stay here till the last person who's needs to leave, but go ahead and ask your question.
Okay, so for the part that says v of t, it's
Uh-huh.
like 3/2 t squared plus 4t. Isn't that 4t supposed to be a 2t?
Oh, yes, it was. I thought I did that in my
Okay.
head and didn't do it on the paper. Good job. Nice catch.
Thank you.
Yeah, I completely, I might even said it out loud, but I didn't write it, so that's not good. Oops. Thanks for catching that. Everybody make sure you correct that as well. That means, oh yeah, okay, so gotcha. Not there. That's what the problem was. Okay. Anybody else have any questions while we're here? Now this one become 2t squared. That 4t, yeah, that was right. I think this 4t was right to begin with. Yeah, that was right to begin with. But over here, it should have been t, 2t. Okay, I did do that. Okay, gotcha. Yeah, not that one. Sorry. All right. Anybody else have any questions? So my office hours are actually after each of my online classes. So 6:40 till whenever on Monday, Tuesday, Wednesday, or Thursday. You can catch me then. You can also that's on Zoom, of course, and I've given you links on that in your Canvas page. I'm also available on Mondays and Wednesdays from 8 to 9. I would suggest you email me and let me know you're coming, because sometimes I'm 8:15, 8:20. If I know you're coming, I'll do my best to make sure that doesn't happen. I also have another one on Monday and Wednesday, usually starting about 10 a.m. It's actually in the lab that I'm teaching on those days. So that's another time. And then there's another time on Mondays and Wednesdays between 1:20 and 2 o'clock. On Tuesdays and Thursdays, I have one that starts around 11 o'clock, and that goes, again, I'm in a lab, but it goes from 11 to about 12:50. Other than that, I can also make an appointment either by Zoom or at school or something like that.
I have a question about the Google Drive stuff.
Yes.
I can't see it. Every time I go to look at it, it says error or I don't have access. Is there
Okay.
something I was supposed to do to get access to it?
I have that same problem.
Okay. Yeah. When the semester started, I got like 3 people that logged in and everything worked for them. I can see that they have access to it, but I haven't gotten any emails like that lately. Let's take a look and see what's going on with that. So I am now going to, hopefully I didn't disappear. Okay. I'm going to share screen here. And specifically, I'm going to go back to this screen and I'm gonna go to my modules. Y'all should be seeing the Zoom screen right now, and it just changed. Y'all see that?
Yep.
Okay, so you go down here. This should be, here's the Zoom meeting for the office hours, by the way. Helpful documents and links. This should be my, oh, Google Docs. Let's see what happens here.
That's
You
there.
get that error, or
Yep.
is it later now? Okay, next click on that.
Click on, what was that?
Up in the top of the gray bar where your window opened, there's a little icon right to the next of the name of that particular window, and click on that. So let me show you again. See that little thing right there?
Yep.
Click on that, see if that works.
Okay. Yeah, I see something now.
Does it actually let you see what I was looking at, which is this stuff?
Let me see. Yeah, I see PDFs. I
Yep.
see some, I guess, Word files.
Yep, that's
Yeah,
it. That's the
I think
one.
I see everything.
Yeah,
Okay.
like right now I'm exporting those notes I just took. I'm exporting it to there. So in a couple minutes, you'll see another one pop up, and it'll be this very notes that I just took. Let's see. Do that. My drive, 241 notes, save here, upload. Takes a couple seconds, but it should be there in a second. And you can again see, notice how all these names are 01, 29, 2023. That's, you know, if you look at the actual YouTube channel, you'll see in the discussion some name like that or name like this, or especially these where it has P241 or PHY241. Those are all from classes, and these are the notes for them. So you have access to all those.
Okay.
Okay.
I
Someone
appreciate
else
it.
said they were having the same problem. Did that help you guys too? I assume it did. All right.
Yep, that works for me too. Thank you.
Cool. Anything else I can do for you guys?
Have a good one.
Yeah, I'll have a nice one. Do check out the examples I gave of motion problems in the actual Canvas page. There's some good ones on there.
Oh, well, I was just like, the last question you did, I was kind of confused. Which one did you like, derivative or anti-derivative? Because I see like the first line
Gotcha.
of the
Yeah,
word used
I
anti.
used the integral on that last problem I did. I actually did an integral twice. But you start off with what's called a differential equation, and that just means an equation that has derivatives in it, and you're trying to solve for what the derivative is being taken of. It's the nature of the beast that when you're in the sciences or engineering, you're going to learn your math in your science or engineering class before you get to it in your math classes, usually.
All right, so where did you see it says X and then the zero, whatever? Where did you? I see you put it like it was. You didn't start. Hold on, I don't know how to explain.
I'll
I
pull
got
it up
really
real
show
quick.
you.
Hold on. That'll help you. So we
Yeah.
can talk about same thing.
So that 5 meters. When did you like? I see the final. You got like +5. Like where'd you get that part from?
Okay, so if you look at the top, it should be showing there any minute now.
All right. I got it written down.
So if you look up at the top, that's my statement of the problem. It says, assume I'm paraphrasing what I said, but the acceleration is a function of time is 3t plus 4. The velocity at t equals 0 is 4 meters per second, and the position at 0 seconds is 5 meters. So when I integrated the first time, I integrated, and this left-hand side became v of t minus v of 0, which is that 4. So that's why I had -4 here. And the same thing happens on this one, x of t minus x of 0, but x of 0 is 5. So I had that. Now, when I solve for x of t, that means this 5 is going to go to that side and become positive.
I'm positive. Okay. All right. I understand. I see where you got it from.
Okay. Now this is it's supposed to be fairly rudimentary integrals, but it is a real integral problem that you will be expected to be able to do on your test. So
Yeah.
that's why I wanted to make sure you guys had seen it.
Yeah, I understand it now. I was just confused from like the
Yeah, and I went really fast on that
Really
last one
fast.
because their time was running out.
oh, that's probably why. But yeah, and got me in the five at the bottom. But I understand now. So
No problem. Anything else for Sherrod?
that's all it.
All right. How about Josh? You got any questions? Or is
Oh
it Josh?
yeah, so my first question is like, is there anything I need to be worried about? Because this is my first class that
Okay.
I've attended. I'm the one that emailed you about the cruise.
Yeah. Gotcha.
Okay,
Yeah.
so what have we done? Like forces? Have we done forces yet?
We have not. We're only in chapter 2, and in fact, all the lectures that I've done have been recorded, so you can go to my YouTube channel and see them there.
Okay, I'll make sure to drop a sub. And are we like? Is there like a general gist of the class that I'm missing? Like, is there something important I need to know? Like, I haven't really looked through everything since I just got back today.
Okay, so yeah, the
Is there anything important coming up?
the next test. Well, you've missed one homework assignment, but I told you that
Okay.
that was going to happen. It's no big deal. You can go ahead and do that when you finish it. Let me know, and I will make sure I give you an extension on that. First set of homeworks, and now chapter 2 homework will be due this coming Sunday. If you need a little bit more time, make sure you check on that or let me know. And then there's going to be a test. Right now, what I think I'm going to do is I'll probably release the test tomorrow or Monday or this weekend, and you'll have until the 10th, which is a week from Sunday, to complete that. It's an online test. You get usually I give you 3 attempts, and I take only your highest score.
Okay, is that test going to be like conceptual or like
It
how's
usually
gonna be?
has a couple conceptual questions, and then the rest are actually problems you're required to solve, algebraically and stuff like that. It
Okay.
will be multiple choice, and it's time. You've got a limited amount of time, but it's open book, open notes, open Google searches. The only thing you're not supposed to do is if someone went into the test after it's been created and posted online, took the test, and then told you what was on it, that would be cheating. Or if they made a web page and put it up and then you went to that website, that would be cheating, that kind of thing. So really, as long as you're not looking at something that someone has created or talking to someone that has actually already taken the test about the test, then it's free. You're open. You're not cheating in any way. Okay.
Okay, and like one more question. I'm sorry, I got lots of
problem.
questions just because I've been here for a little bit.
Yeah, no problem.
So whenever you were doing the integrals,
Mhm.
like instead of just taking the acceleration and just straight integrating it, you wrote it all out. Am I going to be required to do that?
No, I'm trying to do all those steps to show you physically what's going on and mathematically what's going on.
Okay.
If you show me the equation A is equal to dv/dt, and then I see you integrating it, I will know what's going on.
Okay. Well, that being said, thank you. I look forward to this class.
No problem. I hope you enjoy it, Josh. Is it Josh or Joshua?
And either or doesn't
Okay.
really matter.
Gotcha. I'll try to remember to call you Joshua just because you wrote it up there. But yeah, I'm bad with names anyway, so I'm probably gonna forget it.
All right. Bye.
Have a good one.
You too.